Hello everyone, this is Professor Ng Kun from Unimas. In this video, I'm going to give you a lecture on analysis and design of solid slabs. So in general, reinforced concrete slabs form the floors, roofs, and walls of buildings and decks of bridges. Continuous slabs are designed to withstand the most unfavorable arrangements of loads in the same manner as beams, where you have the favorable and unfavorable arrangement of loads on each of the spans of the beams or slabs. Slabs are classified as one-way spanning slab or two-way spanning slab depending on the ratio of the longer dimension to the shorter dimension, which is Ly over Lx, or the support conditions. So if you have a slab that is supported on all the four sides of the slabs, then you look at the Ly over Lx ratio. So the shorter dimension is Lx and the longer dimension is Ly. If Ly over Lx is more than 2, then the slab is classified as a one-way spanning slab. So that means we consider a slab assuming that there are no supports in the shorter dimension. Okay, so the loads will be transferred in one way like this, where the division of loads will be half loads to this support here and half of the load will be transferred to this support there. Okay, and then if Ly over Lx is less than 2, then it is classified as a two-way spanning slab where you cannot ignore the support on the shorter dimension. Okay, so in this case, the load will be transferred in both directions. Okay, where the shorter support dimensions here will carry a triangular load, and then the support on the longer dimension side will be supporting a trapezoidal load. So that is the difference between a one-way spanning slab and two-way spanning slab. And then sometimes when we look at the physical support conditions of the slabs, in a case where you have only supports on this side and this side, okay, there is no beam over here, okay, and there is no beam over here as well. You have only beams here and here. Okay, so in this case, even the Ly over Lx value is less than 2, it is not a two-way slab because of the support conditions, right? So in this case, it still becomes a one-way spanning slab where the loads are transferred to the physical supports like that. Okay, then this becomes the span of the slab, which is spanning one way. So to classify slabs, you have to look at the support conditions as well as the Ly over Lx ratio. So concrete slabs are considered as structural members similar to beams, but it is somewhat simpler because the breadth of the slab is already fixed and the unit breadth of 1 meter is used in the calculations. So what this means is that if you have a slab which is a one-way slab, so one-way slab, you assume that there is only two supports for the slab where the beams are the support for the slabs. Okay, so in this case, the load transfer is this way. So half of the load will go to the beam above and the half of the load will go to the beam below on plan. So in this case, the span of the slab is Lx, the shorter dimension. Okay, and then this is the width of the slab. So the width of the slab is very big. So normally we just take 1 meter width as our design structure. Okay, we just take 1 meter width as our design structures, and then the rest of the slab of 1 meter width will be the same as the one that we have designed for 1 meter width. Okay, and then the shear stresses are usually low in the slab except when there are heavy concentrated loads. So normally shear stresses are very small if the slab is carrying uniformly distributed load, and then compression reinforcement is seldom required in slab design. For design procedure, so we first determine the design life as what we have done for beam design as well, and then we assess the actions on slabs, or we assess the loading on the slabs. After that, we assess durability requirements and determine concrete strength as we have done in beam design as well. And then we determine nominal cover for durability, fire and bond requirements, the same as in beam design as well. And then we analyze the structure to obtain critical moments and shear forces. After that, we design the steel reinforcement for fracture, and then we verify shear, deflection and cracking. Okay, so normally we do not need shear reinforcement, so that's why we only verify the shear stresses or the shear force to be less than the strength of the slab. And then we produce detailed drawings for the construction of the slab. In the analysis of reinforced concrete slab to determine bending moment and shear force may be done either by using elastic analysis or by considering plastic slab methods. However, in this course, we will only use the simplified method based on elastic analysis, and we only discuss on using the moment and shear coefficients for a continuous slab, or for a slab panel which has supports on all 4 sides and supports on only 3 sides or 2 sides depending on the nature of the slab on the design plan. After that, we design the steel reinforcement for fracture, meaning we design the steel reinforcement for the bending moment. So the calculation for fractural reinforcement follow a similar procedure to that used in beam design. So meaning that the design procedure is similar to beam design, except that the width of the slab that we use is 1 meter width, as I have mentioned just now. The first step of designing steel reinforcement for flexure or bending is by calculating K, similar to beam design. So K is equals to M over FCK BD square. And we check K. If K is smaller than K balance, then no compression reinforcement is required. Then we calculate the lever arm Z. So after that, we calculate the amount of steel reinforcement as required for the slab, okay, by using this equation here. After that, we check for shear requirement So shear stress in the slab is subjected to uniformly distributed loads are generally small. It is not usual for a slab to contain shear reinforcement, so it is only necessary to ensure that the design ultimate shear force VED is less than the shear strength of the unreinforced section VRDC, which is given by section 6.2.2 of Eurocode 2, which is equation 5.1 that is listed here. So in this equation here, K is given by 1 plus 200 over D and then to the power of half. And this K value should not be more than 2. Okay, if the calculated value is more than 2, then you just use the maximum value of 2 in this equation 5.1. Same as for this K value, which is to the power of 3 over 2. And then rho 1 is ASL over BWD, okay, where AS1 is the area of tension reinforcement that extends beyond LBD plus D, beyond the section considered. So LBD is the bond length, okay, D is the effective depth, and then BW is the smallest width of the section in tension zone. So in this case, our slab is normally 1 meter width, so BW is normally 1 meter or 1000 mm in equation 5.1. And then D is the effective depth of the slab that we are designing. Okay, so and then for deflection, excessive deflection in slabs will cause damage to the ceiling, floor finishes or other architectural features. To avoid these damages, limits are set on the span to depth ratio, same as beam design as well. So these limits are exactly the same as those for beams. As a slab is usually a slender member, the restrictions on the span to effective depth ratio become more important, and this can often control the height of the slab required. Okay, so in slab, normally this deflection will govern the design. After that, we need to check for cracking. So to resist cracking of concrete slabs, Section 9.3.1 of Eurocode 2 specifies details such as minimum area of reinforcement required in a section and limits to the maximum bar spacing. So the minimum area of main reinforcement is given by this equation here, similar to the S minimum in beams as well. And B normally is 1000 mm or 1 meter width. Okay, so this BT is normally 1000 mm. And then the minimum area of secondary reinforcement is 20% of AS minimum. So in areas near support, transverse reinforcement is not necessary since there is no transverse bending moment. The spacing of main reinforcing bars should not exceed 3 times the overall depth of slab, 3H or 400 mm, whichever is less. So if 3H is more than 400 mm, then the maximum spacing is 400 mm. Okay, if 3H is less than 400 mm, then 3H is the maximum spacing. For secondary reinforcement, the spacing should not exceed 3.5 H or 450 mm, whichever is less. So if 3.5 H, so H is the thickness of the slab. Okay, so if 3.5 H is more than 450 mm, then 450 mm is the maximum spacing of the secondary reinforcement. And then if 3.5 H is less than 450 mm, then 3.5 H should be taken as the maximum spacing of the secondary reinforcement. These rules apply for slabs not exceeding 200 mm thick. So in order to use this 3H or 3.5 H as the limit, your thickness of slab should not be more than 200 mm. Okay, so for slab thickness greater than 200 mm, the procedure for verifying cracking, same to that of beam, should be followed. So if your slab thickness is greater than 200 mm, then you should follow the steps in control of cracking for beams. And then for the detailing, we are using the simplified detailing rules. So general rules for curtailment and anchorage of bars in slab are discussed in section 9.3 of Eurocode 2. So simplified rules for curtailment in different types of slabs are illustrated in figure 5.1 over here. So at the simply supported end, at least half the midspan reinforcement should be anchored as specified in figure 3.21. So at least 50% of the reinforcement required for bending has to be anchored at the supports. Okay. At an unsupported edge U bars in length at least 2H should be provided, anchored by top and bottom transverse reinforcement. So this diagram shows the reinforcement detailing or simplified rules of detailing for simply supported slab. So for simply supported slabs, 100% of the bars for bending has to be provided near the middle of the span, and then near the supports, 50% of what you have at the middle of the span has to be provided near the supports. And then for continuous slabs, so this is a simple support. This is the first interior support. So for interior support, we have negative moments. So negative moments, the tension reinforcement is on top of the structure. Okay, and then positive moment is seen at the near the middle of the span, so the tension reinforcement is at the bottom of the beam. So for positive bending moment, 100% of it should be provided near the middle of the span, and then 50% of it should be provided near the supports. For the negative bending moment, okay, for negative moment, then the tension reinforcement, 100% of it has to be provided to 0.15 L measured from the side of the support, and then you can reduce to 50% when it's beyond 0.15 L and it is within 0.3 L from the support. And then for this part of the beam, okay, at least 25% of what you have here has to be provided at the top of the simple supports in order to cater for nominal hogging moment, okay, or nominal negative moment. Although we assume that there is a zero moment here, okay, but because of the way that we cast the beams and slab together, then we still have some nominal negative moment over here. Okay, so to cater for that nominal negative moment, we use 25% of what we have for the positive moment. Next, we'll look at one-way spanning solid slabs. The idealization of design is as follows. So one-way slab carrying predominantly uniform load, strips of 1 meter, that is beam with a width of 1 meter, is used in the analysis and design. And then figure 5.2 shows longitudinal sections of simply supported slab and continuous slab. So this shows a simply supported slab with a span L. So in this case, the steel that is designed for the bending moment is the one shown in the longitudinal direction. Okay, and then the distribution steels are in the transverse direction. Okay, so meaning that the distribution steel is not designed to resist any moment. Okay, only the moment steel or the primary steel is designed to resist moment. And then we have the thickness of the slab H, and we have effective depth D measured to the centroid of the longitudinal steel here. Okay, so the second illustration here shows the reinforcement for a continuous one-way slab. So this beam, and this beam forms the support for the slab, and we have positive bending moment near the middle of the span of the slab. We have negative bending moment at the support, and then we have positive bending moment near the middle of the span in the interior span here, and then we have negative bending moment at the support, and so on and so forth. If this is continuous, then we have positive bending moment here, and then if you have support here, then you have negative bending moment there. As the slab spans between two supports or beams, the bars in the direction of span are said to be the main reinforcement or moment steel, and are therefore placed nearer to the bottom of the slab. These main bars will be calculated for size and spacing. The bars in the transverse direction are called distribution bars or distribution steel. All slabs must have distribution bars to assist in distribution of stresses. These stresses are caused by the loading, temperature changes, and drying shrinkage. As the distribution bars are tied to the main bars, they also help to keep the main bars in their correct position during pouring of wet concrete into the formwork. So the analysis of slab, in this course, we will be using the moment coefficients. So these moment coefficients are given by BS 8110 Part 1, 1997, and that is table 3.12. So for slab carrying uniformly distributed load and continuous over 3 or more nearly equal spans, approximate solution for the ultimate bending moments and shear forces are given in table 5.1, which is extracted from table 3.12. So if you have continuous structure like this, okay, so this is considered the outer support. This is considered the first interior support, and then this is the interior support. So in this case, the moment at outer support here is 0, and then the moment near the middle of end span, so this is considered an end span. Okay, so near middle of end span here, we have a moment of 0.0 at 6 FL. Okay, and then at first interior support here, we have moment of negative 0.0 at 6 FL. And then middle of interior span, so this is considered interior span. Okay, so middle of interior spans. Okay, so middle of interior span here, we have moment of 0.063 FL. And then for interior supports here, we have moment of negative 0.063 FL. Okay, and then for shear at outer support here, we have 0.4 F, and then no shear at the middle of end span, and then at first interior support, the shear here is 0.6 F, and then middle of interior span, no shear, and then interior support, the shear is 0.5 F. Okay, so F is the total design load per span, which is the total load on one span. Okay, so this is F. Okay, so it is 1.35 GK plus 1.5 QK times L, where L is the span of the structure, okay, or the span of the slab. So that's all for the lecture in this video. We will look at a design example in the coming lecture. Thank you very much for listening.